look at is how to decide where an image will be based upon where it is on the scale here. And so we're okay. So if you remember, this is C, and the distance halfway between C and the mirror is called the focal point. And so we're going to measure that. It's the same as it's been. It's 2.5 centimeters in, right? So 2.5 centimeters, I'm going to mark that. In fact, that's an F. The definition is that F will be equal to, yes, sir.
I'm looking for a regulator.
Okay, sorry for the delay there. So again, yeah, so the focal point is by definition half of the radius of the sphere. And so that's something to note. So when we look at, let's place any random object, I'll place it out here. By definition, it is here, because I just said it's there. The distance from the object to the mirror is referred to as DO, object distance. And we draw the 3 lines, just as before, and I'll go through those real quick. It's not about the image itself or anything like that. Should have made this taller, but that's okay. I'll just do it in parallel, out through F, in through C. I only need the 2 lines. I don't really need 3 lines, but I have a 3rd line in case I have no other ability to do it. In through C, hits the mirror perpendicular, comes back out. So the image is located right here. Okay, the distance from the image to the mirror is called the image distance, labeled as DI. The object from the center line to the top of the object is referred to as the height of the object, HO. The height from that center line to where the tip of the object would be called HI, the height of the image. So we have these parameters we talk about. Now let's talk about what happens if I take this object and slide it towards C. What's going to happen is that the angle between these two, as I move in further and further to the left, this angle is going to get bigger and bigger and bigger, right? And as that angle gets bigger, this crossing point will back up and get further away from the principal axis. Liana? So as DO approaches C, DI also approaches C. That makes sense? So as it slides in. So as DO decreases would be better, DI increases up to a point. And that point is when it gets to F. When DO is less than F. That's something that's a weirdness, and I want to look at that real quick. I don't have one set up to draw this. I'm going to have to sketch it by hand. So I'll draw my principal axis. Get lined up so I can use these lines as a guess line. I'm going to draw my mirror in here. I need something kind of circular. Yeah, it doesn't matter. I'll just guess. All right, and the radius of that is going to be about here. Call that C. Okay. Call this F. So if my object is in here, using the same 3 lines, where's the image going to be? So to do that, we draw our line in parallel to the principal axis, just as before. It will reflect out and go through the point F. I can get it lined up here. It will do that. Then the line that goes in through C hits the mirror perpendicularly and reflects out back on itself. As you can see, the lines out here are going to get further and further apart. They're never going to cross. So there's no way to form an image out here. So what we do is we extend our lines behind the mirror. So here's the one that went through C. I'm going to use a dotted line there. And I've got this one also behind the mirror. So if I see this, these cross right here. the image will appear behind the mirror. It will be upright, and it will be a virtual image. So as the object approaches the focal point, the image, so from outside, if I go from greater than f, as the object approaches the focal point, the image starts backing up. In fact, if DO were equal to infinity, then the image would all of a sudden be equal to f. The image would appear as just a bright dot or a dot right at the focal point. If DO is equal to f, then DI equals infinity. And there'd be no image at all. So this would give me a no image. All right, now, can I truly do this? Can I ever put an object at infinity? Because infinity has no number, right? So the sun's very, very far away. So if I shine the sun at a mirror, it will actually have a size, but it'll be really close to the focal point because the sun's so very far away. Can I put an object at f? Yes, I do. This, if you think of a flashlight, the light bulb is actually placed at the focal point of the mirror in the flashlight, so that the light bulb doesn't form an image on the wall. Otherwise, when you shine a light on the wall, you'd have a picture of the light bulb. All right, and it's just light that's out there. There's no image being created. So there are equations that drive this behavior. Can I do the negative mirror or convex mirror yet? My hour's overlapping, so I don't know if I've done it or not yet. Okay, I have a drawing for that here. Hang on, somewhere. There's one. So here's a convex mirror. What if it looks like this? So if I have a mirror, so this, I'm going to again place my object out here. My center of curvature is behind the mirror. That means my focal length is going to be at the halfway point, also behind the mirror. That's the focal point. So to figure out where the image occurs, we draw our line 1 in parallel to the principal axis. It reflects, it can't go through F because it can't go through the mirror, but it reflects off and comes out as though it came from F. So it actually goes this path. Okay. Then it goes in pointing at the center of curvature, hits the mirror perpendicularly, and comes back on itself. So these two rays, again, are diverging, separating further out. They can't exist. They don't create an image at all. But if we look in a mirror, even if it's curved, we can still see the image. So we extend these lines behind the mirror. The exiting rays extend behind the mirror. And it looks like they combine right there. So for this particular mirror, the focal length is negative. It's behind the mirror. And this is the only way I can do it. The image will always be negative behind the mirror. A convex mirror cannot make a positive DI. Okay? It will always be, and the word is virtual, and it will always be upright. HI will always be less than HO for this particular mirror. Convex can only do one drawing. As I move this object back further and further away, it actually, this angle gets smaller, the image actually goes to the focal point. As I move this forward, the image slides forward up toward the mirror, but it can't ever be outside the mirror. Okay? So for a convex mirror, there's only one setup. For a concave mirror, there are many options I can have. So let's kind of go through those right now. So for a concave mirror, F, focal length is always positive. All right, focal length is always positive. It can't be anything else. If DO is greater than F, but less than C, So the object is between the two. It's between F and C. Then DI is greater than C. It will be real. It will be inverted. All right. So if DO is between, if the object is between F and C, it looks like this. It'll be real inverted, and HI will have a magnitude that's greater than HO. If DO is greater than C, then DI will be less than C, but greater than F. Let me move this over. Then if DO is greater than C, then C is greater than DI, which is greater than F. It will still be real. It will be inverted. And HI will be less than HO as a magnitude. If DO is less than F, then DI is negative, that is to say behind the mirror. Behind the mirror. It will be virtual, virtula, not in Spanish, that's not even Spanish, virtual and upright. Yeah, okay, and HI will again be greater than HO as a magnitude, just the number. So these are behaviors and parameters. If DO equals infinity, DI equals F, it would be real, but HI would be about 0. All right, we couldn't tell if it's upside down or right side up, couldn't do that. If DO equals F, then DI equals infinity, and there is no image because there is no infinity. So these are just parameters that we know to be true for a concave mirror. There is an equation that drives all this. It's a really straightforward equation, but nobody really seems to follow it because it's a fraction. So I'll write the equation instead of deriving it for you. It works for all mirrors, concave or convex. I'm recording it so you can get this video. All mirrors work and follow it's called the mirror equation. It's also called the lens equation. We get the lenses, we just don't change the equation, just change the title of it. And so the equation is 1 divided by the focal length equals 1 divided by DO plus 1 divided by DI, where DO is object distance, DI is image distance, and F is focal length. That is the equation. There's another one for magnification. Magnification is equal to HI divided by HO. And if I do some mathemagic and move it around, it's also equal to negative of DI divided by DO. So we have two working equations that allow us to solve all of these different types of things. I do know that fractions aren't your friend, and so I'm going to rearrange the equation on the left for all of the things we need to know. If I wanted to find F, I have to, before I can find F, I have to add these, I have to add these fractions. I have to have common denominators, right? So to do that, I'm just going to flip over to another sheet of paper here, write the equation again, 1 over F equals 1 over DO plus 1 over DI. Now to do that, I need a common denominator, and so what I would do is multiply over here. I'd multiply this by DI over DI, and I multiply this one by DO over DO. Oh, sorry, thank you. So yeah, I multiply the 1 over DO by DI over DI, and I multiply the 1 over DI by DO over DO. That's just like multiplying by 1. So I'd end up with 1 over F equals DI plus DO divided by DI times DO. And when I invert this side of the equation and invert this side, just raise everything to the -1 power, I end up with focal length equals DI times DO divided by DI plus DO. All right. let's say I want to solve the equation, the original black equation for di. Then I want to subtract. So I start with 1 over di equals 1 over f minus 1 over do. At that point, the f I would multiply by do over do, and the do I'd multiply by f over f. And so I'd end up with 1 over di equals do minus f divided by do times f. And so invert the equations, di equals dof over do minus f. And following that pattern, if I wanted to solve for do, I'd end up do the same math. I end up with do equals di times f divided by di minus f. All right, so these three, if you don't want to do the algebra, these are the equations that you have to keep track of. They all come from the original 1 over f equals 1 over do plus 1 over di. Okay. Okay, let's just start on the packet. I gave you guys a sheet of paper. And we'll get through these. It shouldn't take us very long. So those of you at home can open this up again or just look at it here. I am recording this and I'll post it for you to look at tomorrow. I'll give you a paper copy of this tomorrow if you want. So
Cool.
looking, and note I did not write m equals here because I'm never really, in this I'm not solving for m. I'm solving for one of the others. So starting with number 1, a concave mirror has focal length 18 centimeters. That's f. Where will an image be located that wants to know di when an object is placed 58? So this is do. So I'm looking for di, and if I go to my equations, di equals that version of it. Di equals dof divided by do minus f. So it equals 58 centimeters times 18 centimeters divided by 58 centimeters minus 18 centimeters. So let's look at the other thing I gave you. If, and so for this case, we have do is greater than c, right? So if do is greater than c, we expect this to be true. We expect the image to be in there. So we expect this to be somewhere in here. So what is this number? 26, I believe. 26 centimeters. And if this is 18, this is 36, that makes 26 somewhere in here, right? It says to draw it out as well. So draw a line 1 in parallel to the axis, out through F. Draw it in through C. Kind of misses the mirror, but we'll pretend that it doesn't. And so the image is located here. And that's reasonable. Notice the size of the image appears to be smaller than the size of the object. So we want to use the magnification factor. HI over HO equals negative DI over DO. Solve for HI. HI equals HO times negative DI over DO. So it equals, it says the object is 12 centimeters tall, so 12 centimeters times negative DI, negative 26 centimeters, divided by DO, 58 centimeters. So 12 times 26 divided by 58, no clue, don't remember. 6.5 or something like that. No, 5.5. 26 divided by 58. It is negative 26 over 58. And so we get negative 5.4 centimeters tall. Its H is negative, right? It is smaller. HI is less than HO. The fact that it's negative tells me that it is inverted. Is it real or is it virtual? Well, because it was formed in front of the mirror, it is real. Okay, so we're going to keep the mirror the same and just kind of move through putting things in different positions. Okay. Okay. All right, so we are moving this image, or the object moved from here to here. So DO equals C. So did I do D equals C? I didn't do it. I did if DO is greater than C. If DO equals C, where do you think it's going to be? Where's the image? Well, let's just draw it and figure out real quick where we think it's going to be. DO equals C. In parallel, out through F. I got to go in through F. Can't go in through C. Well, that's one of my three lines, remember? There's three possibilities. In through F, or in parallel, out through F, in through C, out through C, or in through F, out parallel. So if I'm going out parallel, I'm going to see that I'm right here. I predict that the image should be at C. So let's do the math. DI equals DOF over DO minus F. So it's equal to 36 times centimeters times 18 centimeters divided by 36 centimeters minus 18 centimeters. So 36 minus 18 is 18. 18 over 18 is 1. It is 36 centimeters. So the object does appear right below itself. How tall is the image? Well, just like from above, HI equals HO times negative DI over DO. Well, DI is 36, so HO is 12 centimeters times negative 36 divided by positive 36. So this is negative 1, so it's negative 12 centimeters. It's the same size. It's upside down. So it is inverted and it is real. Its height is negative 12. Up here, its height was negative 5.4. It's below the axis where it's formed. So that makes it negative. All right. So here we go. So hang on, I put my glasses down. I can't see what I'm writing. So for DI is equal to DOF over DO minus F. So it's equal to, and again, our DO is 32 centimeters. Focal length remains at 18. So 32 times 18 divided by 32 minus 18. That gives us 41.1 centimeters. How tall? HI equals HO times negative DI over DO. So equals HO 12 centimeters. Kept that the same as all of them. So DI is 41, so it's negative 41.1. I can't write 41.1 divided by 32. And if we do that, we get 15.4. Because up in the earlier problem, number 1, the object is 12 centimeters tall, and they've been keeping the same object. All right. Okay. And then the drawing, oh, by the way, this is negative 15.4. Is the image erect or inverted? H is negative, so it is erect, which is upright. Is it real or is it virtual? DI is positive, so it's real. Okay, drawing in parallel, out through F. I can't do the in through C on this drawing very easily, so I'm going to use the in through F out parallel. In through F. And out parallel. So it's back here behind C. Okay, so that follows the reason. Okay, backside. All of a sudden, DO is less than F. Where should the image be? If DO is less than F, back to this picture. Yes? If DO is less than F, then DI should be negative. It should be behind the mirror. So let's see if our math works out. DI equals DOF over DO minus F. So we have DO 6 centimeters times 18 centimeters divided by 6 centimeters minus 18 centimeters. So I have 6 times 18 divided by 6 minus 18. No clue anymore, forgotten. 6 times 18 divided by negative 12. Negative 9. So it is 9 centimeters behind the mirror. And how tall is the image? Using the same equation, so it's 12 centimeters times negative of negative 9 divided by 6 centimeters. So 12 times 9 divided by 6 is 18. So it is that right? Yep. So it is twice as, no, it's not twice as tall. It's 1.33 times as tall. Yep. So is the image erect or inverted? Well, H is positive, so it is erect. Is it real or is it virtual? DI is negative, so it's virtual. And the image, we draw a line in parallel, out through F, in through C, out through C. They diverge out here, so we extrapolate them behind, and the image appears back here. So if they don't cross in real space, then extrapolate the lines behind the mirror and see if they cross there. Okay, and the last one for today has a convex mirror. Please note, world image form. So DO is 15. Have a convex mirror with a focal length of 18. Please note the 18 is behind the mirror, so it's not just 18, it's negative 18. So the focal length is negative 18 centimeters. So DI equals DOF over DO minus F. The equation remains the same. So it's 15 centimeters times negative 18 centimeters divided by 15 centimeters minus negative 18. Okay, so 15 times negative 18 and divide by the quantity 15 minus negative, so it's 15 plus. And the answer is negative 8.2 centimeters. So that's behind the mirror. And if the focal length is 18, it's less than the focal length, which is good. HI equals HO times negative DI or DO. So it's equal to the 12 centimeters times negative of negative 8.2 divided by 15. So divided by 15 times 12, 6.5. So just over half as tall. Is it erect or inverted? HI is positive, it's erect. Real or virtual? DI is negative, it's virtual. Drawing, line 1 in parallel to the axis. Reflects out as though it came from the focal point. Extend the lines behind the mirror. Line 2 points at the focal, or excuse me, at the center of curvature. Reflects off on itself, goes back out, but extend the line behind the mirror. They crossed right there. That's the image location. Okay, any questions?